Yeah, it's a great pleasure to introduce Julian Schmitt today, because it's not very often that you can say that you're introducing someone who has produced a new state of matter, although maybe not of matter. We will find out how to think about it. So Julian was part of the team of people that created the first photon BSc, which happened at the University of Bonn, where Julian got his undergraduate studies and also his PhD. He then moved on to the University of Cambridge, where he actually worked on atomic Bose-Einstein condensates, looking at the BKT transition, looking at two-dimensional physics in the system, and found a number of fundamental new insights on the BKT transition. He then actually returned both to photon and to photonic liquids and to Bonn to start his own group with an ERC starting grant, where he has now been working on extending this very interesting quantum simulation platform, which for me I'm particularly excited about because it does capture dissipation in a way which, of course, when looking at real materials is key. And his work has been rewarded in a number of ways, including the Rudolf Kaiser Prize for Fundamental Science and the 2024 prize of the Akademie der Wissenschaften und Künste. And now I don't want to take up any more of your time. We're very much looking forward to your talk today.
Yeah, thank you very much for the introduction, Gregor. It's a real pleasure to be here at EPFL. It's my first time in Lausanne and first time at EPFL. It's kind of obviously same statement. And yeah, so far I really enjoyed it, and I'm looking forward to discussing more during the day and learn more about the research that is being conducted. So in my talk, I want to present you experimental work that we did over the last few years, where we investigate quantum gases, optical quantum gases. So these are gases of many particles which are operated in the quantum regime and which are consisting of particles of light, photons. In our case, pure photons. And I will show you that in these experiments we could now really use this system a bit like a material and probe bulk properties of the system, such as the compressibility and the equation of state, which are very fundamental properties of a material. But to start with, it's not working now.
Sometimes after you put zoom in to click on your slides once.
Okay. Yeah, now it's working. Okay. So imagine, to start like slowly, imagine if I would give you an unknown substance, it could be a gas or a liquid, you don't really know, and ask you to characterize this material. Of course, you are all working with some solid state systems, and you could perform some elaborate technique like perform spectroscopy also, but the most immediate thing that you would probably do is just take it and squeeze it. Yeah? So what you do is you apply a force to this material, you increase the internal energy by reducing the volume of the system, and in this way you actually perform a measurement of the compressibility of the system, and the system will of course respond in a different way if it's a piece of stone or if it's kind of a very fluffy material. Turns out that this very simplistic approach is a very valuable tool to identify quantum states of matter, also classical states of matter, and phase transitions between these systems. And from a material particle point of view, we understand the compressibility fairly well. So here are some paradigmatic examples. In the solid state, for example, an incompressible system is the Mott insulator, where I have one particle sitting at the different sides of a lattice, and it costs me quite a lot of energy to put two particles on one side because they are repulsively interacting. So there's a charge excitation gap in the system, and it makes it basically suppresses fluctuations and makes the system very hard to compress. Similarly, in superfluids, for example helium-2, the interparticle interactions are so strong that it's very difficult to bring two particles close by because they are repelling each other very strongly. So also here this system is fairly incompressible. What is already different is if you create a quantum gas of ultra-cold atoms, here we have tools to control the magnetic field and tune the interactions between the particles. So the system can either be strongly interacting or it can be already moderately interacting, which may increase the compressibility. What I want to emphasize here is that this property is extremely fundamental. Yeah? It determines the equation of state of your material, so it tells you how the material behaves. It tells you via the fluctuation-dissipation relation how are fluctuations occurring in the system, and for example also what are the transport properties such as sound propagation in the system. What has not really been known so far is what about light matter systems? I call them optical quantum gases, and specifically this means condensates of photons or polaritons. Here we don't really know what are the properties of these systems in terms of the compressibility at least. Why? Because it's very hard to prepare them actually under equilibrium conditions. Also, it's very hard to create a systematic trapping potential, for example, where you could probe all of these properties. But in principle, a very large compressibility would be expected here, and in order to just get a feeling from the textbook what happens in such a Bose gas if interactions are very weak, here is an isotherm of the ideal Bose gas, in this case for 3 dimensions, so pressure against volume. If I prepare my sample at a temperature T and I lower the volume, I basically compress it, I see the pressure increases and eventually there's a critical volume where the system undergoes Bose condensation, and beyond that something particular, or let's say a bit strange even, happens. Namely, the pressure does not increase any further. So it means I can add, without adding any energy to the system, I can add more and more particles, so this curve actually becomes flat, and in other words the system becomes infinitely compressible and in this sense also thermodynamically unstable. In any real system, of course, you have repulsive interactions, U, which actually restores the finite compressibility. So if you lower the volume, actually this pressure will further and further increase because the particles, of course, now bring in more repulsive energy. And still the question stands, is this ideal Bose gas in general actually a physical system? And here I want to quote a famous theoretician who probably many people of you know, Kwasum Hwang, who wrote a book on statistical mechanics. Just as an info, he wrote that, of course, before the first realization of a Bose-Einstein condensate. And he writes, well, the ideal Bose gas is an artificial example in that particles condense into a highly idealized phase with infinite compressibility. That is, the Bose-Einstein condensate is unphysical and uninteresting. So that's a bit of a demotivating sentence. I would definitely say that uninteresting has been ruled out with the first observation of a Bose-Einstein condensate. But what of course still stands is, what about, is it actually a physically relevant situation? And here we can ask the question, if we go to low interactions, now with these highly controlled optical quantum gases, can we learn more about this part of matter, or this state of matter? So our approach is pretty basic. We want to create a system that is as systematically controllable as possible. So we want to take photons, which in some sense is our material. We want to contain them in a box trap, in this specific case in 2 dimensions. So these experiments in general are only possible in lower dimensions. And that in the end will give us a well-defined volume and a uniform density, such that we can really test the bulk properties of such a gas of light, basically a photonic material. So in recent years, these uniform 2-dimensional Bose gases really have led to novel insight across the field of quantum gases. On the one hand, in ultra-cold atoms, we are able to contain cold atoms inside a basically sculpted box of laser beams, which acts as a repulsive potential. And then this has been used by us, but also, of course, in other groups, to study first and sound propagation in such uniform samples across the topological Berezinski crystals. Soulless phase transition to a superfluid, and at the same time also drive the system away from equilibrium and really in a systematic way see how does turbulence, for example, emerge. Then going away from these quasi-equilibrium conditions to the German dissipative systems, a famous platform are exciton polaritons. I will talk a bit more about it in the following, but here one can also realize uniform gases by creating a repulsive barrier by irradiating laser light, which is also shaped as this rectangle. And people have studied, for example, the topology of exceptional points, features that occur in open systems, sound propagation as well, and critical fluctuations in the vicinity of a phase transition. In this talk, I want to kind of reverse the paradigm and not contain a material inside a trap out of light, but I want to contain light inside a trap that is made out of a material, so specifically in a type of a mirror box, so a shaped optical cavity. And I convince you that in this system we can indeed study Bose condensation phenomena as well as compressibility and equation of state experiments. Okay, so what are these optical quantum gases? Just as to get us all on the same page, there are two main platforms in which collective effects in systems consisting of light and matter are investigated. First, on the side of the strong light-matter coupling, we have exciton polaritons. So here you have an exciton localized typically in a quantum-well structure inside a fabric mirror cavity. So these are Bragg mirrors where a photon is stored, and through the coherent exchange of energy, these two species are hybridizing and form a polariton. And in a series of experiments in labs across the world, condensates of these exciton polaritons have been realized. Notably also, one of the first results was in part achieved here at EPFL, where then the light that leaks out of the cavity, which is reminiscent of the polariton field, is concentrated at small transverse angles. So this here is Kx, Ky. So basically this is the light that comes out of, as a cone, comes out of this cavity. On the other hand, in the weak light-matter coupling regime, we just consider photons, and this is the part that I'm going to talk about. So here we also have a material component. These are excited dye molecules, and we have photons, but they don't couple, they don't hybridize, so they are independent of each other. Nevertheless, also here condensation effects can be seen, and this comes about from the fact that the photons are trapped for a long time in this cavity and thermalized by contact to the molecules. So the attractive prospect of this system is that you can really study BEC physics and more at comparatively high temperatures, at approximately 4 Kelvin for these systems, up to room temperature for these systems. And I want to tease you a bit more with what are the directions of this field currently. So can we create novel states of matter using these systems actually, or maybe even dream of having devices? And one of the big directions certainly is to explore topological photonics, to be able to create structures where you have a localized edge current, for example, that is not scattered by defects. And in particular, our team is looking at inducing such topological properties solely by non-Hermitian effects, so by controlling the coupling to the environment, by adding locally gain and loss to the system. Then you can also have a completely new conceptual look at thermodynamics using photons and study effects that have not been investigated before. Here's one example, for example, of a measurement of the specific heat as a function of temperature, where you see nicely this cusp-like divergence of the specific heat at the Bose-Einstein condensation critical temperature in 2 dimensions. Then there are more and more efforts now going into the direction of using coupled systems of condensates for Hamiltonian simulation as well as physical computation, because you can actually map these systems here on spin glass systems, and they again can be shown to fulfill a certain complexity class for computational problems known as NP-hard. Then we can couple these condensate systems of light very nicely to the environment. This allows us to study open quantum systems. We have a system and some reservoir. This reservoir can be lossy, but it can also bring particles back, so it can also be actually providing gain. And finally, an interesting new direction also is the investigation of emergent phenomena. So what type of collective dissipation-induced phases can we have in such complex grids? So this is experimental data really in these kind of lattices of condensates, for example, large-scale vortex structures that can be formed, or mechanisms for novel type of BKT-like superfluid phases. So with this, I would like to come to the outline of my talk. In the first part, I would like to discuss how do we create optical quantum gases in the box, and how can we measure the compressibility and the equation of state. And then in the second part, move on a bit talking about the open system control of photon BECs. In particular, we were able here to study for the first time a fluctuation-dissipation relation in the context of a BEC in this type of setting, because we can control and couple our condensates to the environment. So how to realize such an optical quantum gas? Well, you need a container for the light, right? That's the starting point. And what you use is, we call this an optical microcavity. So it consists of two highly reflecting mirrors. This is, of course, an artist view. Yeah? And the light, as you can see, it's not really straight beams in between, but it looks more like a cloud. And why is that? Well, it means that there are some kind of thermal properties imprinted on this photon cloud. And how does that happen? Via the coupling to a piece of material. And in our case, these are dye-molecules. So the photons propagate here. They are absorbed by the molecules and re-emitted. In fact, there are very many of these molecules, 10 to the 9, just in the volume of a single cavity mode. More conceptually, such a photon gas operates as follows. You trap the light in a highly reflecting cavity. For the purpose of this illustration, I'm just choosing two spherically curved mirrors. And the reflectivity of these mirrors is pretty good. So the finesse, if there's nothing inside, is on the order of 10 to the 5. So a photon stays there for 10 to the 5 round trips, approximately. Then you insert the dye molecules in a liquid solution, you excite them from the outside, and such an excited molecule will actually emit a photon at frequency omega, and then see the next molecule will absorb this photon and re-emit at another frequency, omega prime. Then meet the next molecule and emit another photon at omega prime prime, and so on. So there's a cascade of absorption emission. The photons do not leak out of the cavity, but they are first cycled through the material many times in an incoherent fashion, however. So this absorption emission cascade then leads to a thermalization by repeated absorption emission processes. And this can be understood microscopically here in my simplistic dye-molecule toy model, where you can see the electronic ground state with many vibrational and rotational states on top, and the excited state. So I can excite this molecule with a photon of frequency h bar omega, and then it will relax via dissipation of some excess energy to the environment, and emit from, in general, a different state to a different state also in the ground state manifold. What is important is that this process, the rate for absorption and the rate for emission, they actually scale with a Boltzmann factor. And it's very crucial because this Boltzmann factor, after the photons undergo many absorption emission processes, is imprinted on the photon gas. So this relation is for dyes known as the Kennard-Stepanov relation, but it actually has also been observed in the solid state. So for semiconductors, it's commonly known as Van Roosbrugge-Shockley relation.
Sorry, in what does this differ from the black body, from the image of black body radiation?
Yeah, that brings me exactly to the next bullet point. What is different here to the black body is that you have an energy offset. So you introduce with this molecule, you introduce an energy gap such that you cannot excite or put in excitations by increasing the temperature. So I cannot just increase KBT and hope to have more and more photons in the system, but I actually separate these two energy scales, because this here is in the visible domain, whereas KBT is like a factor of 100 smaller. So it's basically, we kind of decouple the Stefan-Boltzmann law, photon number and fourth power of temperature does not hold anymore.
In a sense, also in the black body radiation, there is a decoupling which is related to the quantization. It's a different kind of decoupling, okay. But that's what kills the spectrum in the ultraviolet, right? It's the fact is the quantization of the harmonic oscillator is the fact that you can't have.
Yeah, okay, but Stefan-Boltzmann law, I think we agree that this holds, and it's basically here kind of lifted. So you can independently control the number of excitations. That is a very good question, because in the end, the idea is to create something that's very close to a black body radiator, but just introduce this gap. And the cavity also introduces a ground state energy, which is on a similar order, also 1 electron volt, let's say, which you cannot excite by KBT, which is 1/40. Right. So that's essentially a very good question, because it really points to my last point here, that you have a non-vanishing chemical potential for the photons. due to this energy offset.
May I disturb your talk just to understand? So that the fact that you can even talk of a chemical potential is again related to this to this gap, because otherwise the number of photons is totally free, because you could just have no linear effects like Chi2 and multiply or divide the number of photons. So the fact that you put this gap means that now your photon behaves like as if it were a particle that can't just so it's a quasi-conservation number of particles, essentially.
Correctly. Well, absolutely right, I agree.
Yeah, okay.
So an excited molecule is the same as a photon.
Yeah, exactly. Okay.
And this will be important later when it comes down to this reservoir engineering and so on. Perfectly. Right. So a second ingredient that is important in these cavities is that we're dealing with two-dimensional systems. So this you can see typically a photon. Well, it's the ground state of a photon is actually at energy of 0 at wave vector equal to 0. Follows, of course, this dispersion relation. It's just a straight line. But if you now go into the environment of a microcavity, you have a boundary condition that is pi q over, let's say, the length of the cavity, where d0 is just some spacing, and delta d is the variation transversely of maybe the cavity has some curvature and so on, as I was showing before. And this d0 is a very small number. So it's, maybe I didn't stress this enough on the last slide, but it's actually 1 micron. Yeah, so the cavity mirrors are spaced by 1 micrometer. So it's on the order of the optical wavelength. That's very important because it allows you to tailor, expand here this root expression. And you obtain these terms, specifically which are a bit meaningless here with all these prefactors. You don't really know what does this mean. But then identifying this term actually with an effective photon mass, you can see that there's some physical meaning to it. There's a rest energy term, a kinetic energy term, and finally also a potential, a repulsive potential that depends on the local cavity length. So the photons have an effective mass in the system. They are kind of quasi-quadratic. They have a very light mass of 10 to the minus 35 kilograms, so much lighter than an electron. 4 orders of magnitude or so, or 5 actually. And the microcavity geometry allows us to then play with trapping potentials. So here's a view in the lab to give you a feeling for it. So it's a pretty standard quantum optics experiment actually. So there's quite a lot of mirrors and lenses and so on, which means we have quite good control over these systems. So we can manipulate them, we can read them out nicely. And the physics, however, you see it's a big table, but the physics just happens in this small volume. It's a very small spot. And the cavity mirrors are shown here, so we can kind of have to grind them to smaller size to really, in the case of a curvature, push them to close separation. And here you can see a view on the assembled dipole cavity. There's a bit of fluorescence coming from the LED. That's not how it looks like in the real operation, but I guess it gives you a feeling for these experiments. Now, using this setup already almost 15 years ago, we were able to observe boson condensation of photons. And this transition really happens at the expected, thermodynamically expected critical particle number of 80,000 photons. And several types of evidence for this have been investigated over the years. I just want to highlight maybe here 2 examples, which is the spectral and spatial distribution. So you see this is the energy and this is the signal. These are 4 different spectra shifted vertically for increasing total number of particles. And here you can see Boltzmann-like distribution. So this is an exponential decay. And if we increase the total number of particles, the additional photons are occupying the lowest energy state that is available in the system. So not just some state that has maybe favorable gain and loss, but it's actually the lowest available energy state. So it's driven by an energy principle. The photons really want to minimize their energy. And the condensate can also be seen as a bright spot here in the center of the trap. That is because we have, for these experiments, 2 curved mirrors, and 2 curved mirrors, as I said before, map onto a trapping potential, in this case a harmonic trap, where of course the ground state is localized in the bottom of this parabola. Then we also looked a little bit at the dynamics of how does the system actually go into thermal equilibrium if you first prepare a non-equilibrium state. For this, we looked at the redistribution of a wave packet to this BEC via contact to the dye molecules. And here you can see a sketch of the scheme of this experiment. You prepare a wave packet. So these are basically coherently phase-locked excited states. And this wave packet will oscillate now in the trap with the trap frequency, which is a period of 27 picosecond. So it's 40 gigahertz trap frequency. So you can think of this a little bit as a non-equilibrium, like a mode-locked laser that goes back and forth. But however, this system is then redistributed into the ground state after actually the molecules have been homogeneously excited. So this is during the first 20 picoseconds, this wave packet travels, it's reabsorbing, or molecules reabsorb the photons, and that gives rise to the emergence of a BSC then in the lowest energy ground state. The thermalization time can actually vary and depends on system parameters. It can be from 1 picosecond to 1 nanosecond. In general, 1 nanosecond is just an upper cutoff given by our cavity, so we cannot store light for longer than a picosecond. But of course, I promised you to go to box potentials, uniform systems, and not talk about harmonic traps. And the first thing that you need to master or control is to actually be able to control the geometry of the cavity in a variable fashion. And for that, we use a surface structuring technique for dielectric or high reflectivity dielectric mirrors. You can see the surface of one of these mirrors. Here's a scale and several structures that we imprinted on it. If I zoom in, you can see nicely that this is kind of a square-shaped system. In this brighter region, we just locally elevated the surface of the dielectric mirror. You see it's a delicate structure that's actually much smaller than human hair, of course, but still nothing compared to all the nanophotonics tools that one has around. So this is pretty good for our standards, but of course there may be actually even better ways to make this more precise. What this amounts to in an assembled cavity in the end is that you have this structured mirror and a flat mirror, and depending on this local cavity spacing, as I said before, this will then lead to conservative repulsive barriers here at the edge, and our goal is to trap the light in between and create a uniform gas in this box trap. How is it implemented? Just a few technical remarks on this. We use this laser-induced surface nanostructuring technique, often also called delamination. We have a mirror sample that contains a thin 30 nanometer thick silicon layer, and then you use a laser beam that you actually steer across this silicon layer, which absorbs quite a lot of this light and deposits heat. Very specifically at this point, of course, there's a bit of diffusion and so on, but effectively it leads to a buckling up of the dielectric layers, and this is due to the release of mechanical energy that is stored in this tantalum pentoxide films that are basically every second dielectric layer consists of this Ta2O5. And it's also connected to the formation of pores in the lowest lying states, lowest lying layers, which however does not affect the higher dielectric coatings. So then after scanning the laser across a path, you can imprint such a surface profile. Of course, this maps to a two-dimensional box potential, and the slope width here is on the order of 3 micron. We get a surface roughness in the central region, so this is just the unmodified mirror of 0.4 angstrom, so that's pretty good. Actually, the glass is coming from Switzerland, so someone really polished it very well. So it's 0.4 angstrom. That amounts to 50 gigahertz of potential noise on the bottom of this potential, and it's a good number because our ground state, the lowest lying energy state here, is 17 gigahertz. So it's a bit higher. So we don't expect it to be much deteriorated by the noise that we have in the bottom of the trap. And additionally, the height of these barriers is limited. It's 25 nanometer, which gives us a trap depth of 1.4 kVt. Now, in order to study this, we assemble this cavity again, putting together the mirrors, dye, and injecting the photons from the outside as an effective excitation, which then populates and thermalizes into the mode structure of this box cavity. The light partially leaks out of the cavity, so we use a microscope to collect both the real space surface density, here as a function of position, which is very nice and flat. It's a very homogeneous photonic sample, if you want. And the density is somewhere smaller than 1 photon per micron squared, which is actually in the normal gas region. So there's nothing quantum yet in there. Then at the same time, you can look in Fourier space and obtain a momentum space distribution up to the trap depth. I told you this potential only has a finite depth. So So there's actually a cutoff, a maximum wave vector up to where the photons can be observed, and in there you nicely see a Gaussian distribution which has a width of effectively 300 Kelvin. So we here are able to create a uniform gas of light at room temperature, and the first immediate question that you want to ask yourself is what happens if we increase the phase space density, if we put in more and more particles into the system, which we can do easily. You can see indeed that at first for small photon numbers around 1 to 3,500 we see a nice flat top distribution, which then eventually is deformed. You see more density is visible in the central region, and eventually it's dominated by a sine squared function, which of course is the ground state of the box potential. So that means that the particles here really macroscopically occupy the lowest available energy state in this box potential. The same is visible in momentum space, where there's a transition from a Gaussian distribution to this kind of bimodal behavior, where this here is the kx, ky equals 0, 0 mode. Now, where does it happen exactly? You can start counting how many of the photons are sitting in the volume of the lowest k mode, and how many photons are sitting in the excited k modes, and then you see nicely here the population is a function of the total photon number, how actually there's an increase of this condensation at approximately 3,500 photons, and also the excited modes saturate. So every additional particle that is added to the system goes into the ground state. Finally, the system sizes that we can realize are not just fixed. So this is a 40 by 40 micrometer sized box, but we can also go to 80 by 80 micron or 90 by 90 micron. And this is what we do here, and our motivation to do that is the following. In a two-dimensional system of bosons, which are uniform, you actually do not expect boson condensation to happen, because there are always long wavelength fluctuations that destroy long-range order. But we observe condensation here, and how does that fit together with this typical description of the Mermin-Wagner theorem? Well, we test this for different system sizes, and we see actually nicely that the critical particle number scales not only with L squared, but with an additional factor of log L. And this logarithmic term comes from the finite size effect. So it actually ensures that if L goes to infinity, also NC goes to infinity, meaning that the critical temperature goes to 0. Yeah. So it's all good. Thermodynamics is still right, and these are finite size effects. So how can we test now the bulk property of such a gas? How can we compress this system? And it turns out that it's a fairly straightforward thing to compress a gas of light in these open access cavities. You just have to tilt one of the cavity mirrors. That then induces a linear potential gradient that is superimposed with your box potential. It actually really pushes the gas of light, which is here unperturbed, to the side, as you can see here in this forced scenario. And from this center of mass displacement, after some calculation, you can actually find, so this uses the local density approximation. Maybe I should just note that here, and if you have questions, please ask me. This center of mass displacement is actually so the weighted integral over the density distribution normalized by the total number of particles, and you find then that it's actually proportional, directly proportional to the compressibility. So if there's a lot of displacement, also the compressibility is large. Or you have applied quite a strong potential gradient, so it forced the system quite a lot. So this is just a single snapshot. Of course, we can do this more systematically. Yeah.
Excuse me. Can you comment on how are these measurements actually done, the spatial distributions?
Yeah, so this is really just imaging, optical imaging, using a camera. In this case, EMC CD camera, so it's quite a sensitive camera. Just direct imaging with a microscope objective that looks onto the sample and then magnifies onto the chip. Here I don't show any momentum space distribution. Momentum space is done in the Fourier plane. So you go basically somewhere there's a focal plane, and you put your camera there essentially.
Are these experiments done in a continuous way, or are they really dynamical experiments where you inject light, you wait for a thermalization, and then you what happens?
It's the latter. We're not doing this dynamically, otherwise we would be in a completely different regime, because we could really start doing Carnot cycles and so on. We cannot do this here. It's all quasi-static, so basically what you do is you tilt and you wait for the system to thermalize. You take basically.
Yeah, but I mean in general, even without tilting. So this is something where you jet the light,
yes.
you have some time for thermalization, and then you observe.
Yes. Yeah. So it's the system is not really continuously operated. It's operated for 1 microsecond or so. Then we turn it off for a millisecond, but that's due to technical reasons. But effectively, it integrates over all the photon dynamics are integrated out, which is this picture of the stationary distribution, steady state distribution.
But I mean, it's integrated over the integration time. The driving field is on or off.
The driving field has to be on, because otherwise we lose. I mentioned it earlier. After a nanosecond, you always have to fill up the excitation, because you continuously lose what we measure. We have lost essentially. Yeah. So it's a steady state. Okay, so now using this method and applying different potential gradients, you can really extract different center of mass displacement. And here are 2 examples. One for a gas that has a normal condition, or that is far below the condensation threshold. So below means it's classical. And you see that the center of mass response is quite weak. It does not really change a lot. And the applied gradient, and it's linear basically over like something like 20 to minus 20 Kelvin. Remember, the system is at 300 Kelvin. So that's kind of the units of the system. But then if you go further and further towards the quantum degenerate region, where you still have a flat top density distribution, you actually see that this becomes highly nonlinear. So it becomes very sensitive. Already small tilts of your box will displace your density. That is also well understood. So the linear regime is actually determined by the energy scale. It's either KBT or the chemical potential, which becomes very small here for this green data. So here we have to be very careful and just use the linear part. And doing this now for many different densities, we can reconstruct from the slopes the compressibility of the photons. And this here is really the first measurement of the compressibility of a gas of light across the classical and quantum gas regime. By changing the density. You see at first it drops, it goes down, because you add more and more particles. So there's more and more energy in the system, and it becomes harder to compress this system. And then eventually there's a turnaround point, and here we have a transition from Boltzmann statistics to Bose-Einstein statistics taking over. More and more particles actually go to the lowest lying energy states in the system, and that changes the compressibility behavior, until at this green point, or shortly behind it, the system undergoes Bose condensation and the density becomes inhomogeneous. And by integrating this curve, one can actually see now, from my introduction, remember there was the PV diagram for a 3D system, that actually here in a 2D system you kind of get somehow a kink, but unfortunately I don't have the data to compare, because this is something that I did yesterday on the train, to establish some connection to the introduction. So there's really this resemblance of a part which is very flat, which comes about from this sharp increase here. It's really there in the system. And if the system would be larger and larger, then we would expect here the data to follow this dashed theory line. Okay.
Just to make sure, so the photons are not interacting, so you would expect the compressibility to diverge then with these.
Yes, well, we don't really...
In an infinite system.
Yes, exactly. As you can see here in this dashed line, it becomes like it just goes up and up and up and up. But I wouldn't call it a divergence, because it's not really at a critical point, but it rather just goes to infinity.
Yeah, just going to this, so then...
Yeah, exactly. So all the effects that we see with condensation are just finite size effects. So when we go to larger and larger system, what happens actually is that this point here is just postponed to higher and higher densities. You shift it and you start reconstructing the ideal Bose gas equation of state. And this is what we also measured then. The equation of state, of course, being well characterized in many different settings, from bosons to fermions in cold atoms, for example, all kinds of dimensionalities. Here we measure this for a photon gas, and we find a good agreement with the 2D Bose gas description. Essentially, we again use the same energy meter by tilting the cavity and looking for the density distribution. And all this data that you see here are always snapshots of the density, which we stitch together. And we have a very well calibrated energy scale. So we know exactly how broad, how does X map on chemical potential because we know exactly by how much we tilt our cavity. Okay, so with this, I want to actually move to the second part of my talk, and I don't have so much time left, so I hope to do this. And talk a little bit, go away from these homogeneous systems and now discuss more the aspect of open system control and coupling the light to reservoirs, and looking at the first time here at the fluctuation dissipation relation, which of course is a very central aspect of statistical mechanics for equilibrium systems. So coming back to the image from before, I think really one of the attractive features of this platform is that you can create reservoirs and that you can engineer them in size and so on. So why is that? Because you have photons stored in the cavity that are always interacting with the ground state molecules and excited state molecules by emission and absorption. And effectively these excited molecules, as we discussed beforehand, they can be considered as a particle reservoir, effectively. So like a stored photon that is now, has the form of a molecule, but it's actually just a photon, you know. And from the outside, you can control how many excitations are in the system, so how many excited molecules and how many photons do I have. And what is the physical origin of that? It's, of course, a photochemical reaction that comes from this absorption and emission. So I can take a ground state molecule and a photon, which is at frequency omega c, and I can convert them in an excited state molecule at frequency omega naught. And typically, this the tuning here is a number that is smaller than 0. That's just, again, a technical aspect, but it's important to note. So a photon costs less energy in the system than an excited molecule. And this system, obeying thermal equilibrium conditions, of course, it tries to minimize its free energy. And the free energy is a function of the energy created by generating photons. So this is a negative number because the detuning, as I mentioned, is negative. But of course, every time I create a photon, I also take out an excited molecule, and that actually reduces the entropy that I can put into this ensemble of molecules, which is just here n factorial over all the different combinations of excited molecules which are indistinguishable and ground state molecules which are indistinguishable. So minimizing this should actually tell us how does the system respond to a change in the cavity length. And let me show you that this directly will lead us to the fluctuation dissipation relation. So what is the probability now to find n photons in a condensate? Here's the probability distribution, and you see this prefactor here is nothing else but the entropy, actually. Yeah, so this is e to the log of these factorials, and you have an exponential which contains the energy, which depends on the number of photons and the detuning. And of course, using such a probability distribution, I can calculate the kth moment for the photon number, and in particular the second moment. That's a very important quantity in quantum optics because it tells you actually what is the G2 function. So what is the amount of fluctuations that are in your system. And now if we have a small number of molecule excitations and compare this to a relatively large condensate population, you see that the G2 function is essentially flat. This corresponds to suppressed fluctuations. As you see here as a function of time photon number. This is essentially a quiet BEC that obeys Poissonian number statistics. So very much comparable to the characteristics of a laser. However, if you engineer a larger and larger reservoir, which now can exchange particles with the condensate, you can see here in these experiments we indeed observe a bunching of the condensate, so strong fluctuations. And in the simulation of this BEC here, you see how it actually flickers as a function of time. And this corresponds now to the other limiting case of this function here, which is Bose-Einstein statistics. So this we already did a while ago experimentally and could confirm that these grand canonical conditions are indeed relevant. But the question that was still standing, what is the nature of the fluctuations? So by which energy scale are they actually characterized? So in the end, we were after this exponent here. And in order to be able to measure it, you need to, on the one hand, measure correlations, G2 function, and at the same time do spectroscopy. And this is the scheme of the experimental setup. You have a cavity you get the light, couple out the light, send it on a grating, and then record it on a street camera. So this street camera nicely shows you if you have random emission or bunched photons. So this would be the grand canonical case, so large reservoir. For a small reservoir, you have Poissonian statistics. So this is actually realized by controlling the energy cost for a photon. So you tune the cavity length, and that sets the energy cost for a photon. If you make it very long, the photon will be more readily tuned and cost not so much energy to create it, whereas it will be energetically more costly if you go to a short cavity. This behavior then directly connects to the fluctuation dissipation relation, because for a large detuning, you can see here the dashed line as a function of the detuning shows you if the cavity gets larger and larger as we go from right to left. At some point the system chooses to produce many, many photons, which we can measure, and we can also spectroscopically determine what is their change with the detuning. That gives this response function. At the same time, look at the fluctuations. If you do the math, essentially you can measure both sides, or you can map out both sides of this equation here. You see this is the variance G2 function in terms, or in the language of a quantum optician, and dn over d delta, which is just spectroscopy. So how does the condensate population change if I change a little bit the cavity length? And this is what we did here in this very narrow spectral region of only 30 gigahertz, so it was a very challenging experiment actually. And you can see nicely that when I rescale with KDT, setting t equal to 300 Kelvin, my response function, I see a very good agreement between both sides of the equation here. But I can also, of course, use both independent measurements to determine what is the temperature of the fluctuation. And here we find a value of 271, which within the error is consistent with room temperature, where the system is operated at. Finally, in the last minutes, I want to also highlight that, of course, this cavity is not a perfectly closed system, but there's also dissipation out of the system. Photons are constantly leaking out due to the mirror transmission. So we need to slightly modify our description. We now also have a loss channel of the photons. They just go out, which requires us now to continuously pump the molecules. So we continuously need to fill in the excitations that we lost from this mirror loss. And also we are able to pulse the system and look for temporal response dynamics after changing the number of excited molecules in a controlled fashion. And that I think we used for a quite nice study very recently, which was, does the regression theorem actually hold in this coupled system of a BEC and a reservoir? So what is the regression theorem? Basically tells you that the two-time correlator, like a G2 function for example, should obey the same dynamics as a single-time response. So in simple terms, if I let my system fluctuate and analyze the G2 function of time or position, it should have the same characteristics as if I hit it. And that was what we wanted to do now, actually perturbing the reservoir of molecules, which by light-matter coupling is talking to the Bose condensate, and then look for the average response, then immerse the reservoir into a fluctuating bath and look for what are the correlations, and finally hit it very hard. You see the spring is suffering bad because it's becoming anharmonic, the system. So there is some nonlinearity in the system for sure, because it's basically a saturation of the molecules. And we wanted to bring all this into one coherent picture. And to do this, you need to consider the equations of motion for the photon number variation, which is given by this partial differential equation, which couples the photon number and the molecule number variation with a non-Hermitian matrix. Non-Hermitian just means the eigenvalues of this matrix in general are complex numbers. And here, because it's a linearized equation, it looks a little bit like a harmonic oscillator, which, however, is controlled by the number of condensed photons. So if I have a photon condensate which only contains 2,000 photons or so, and I hit it, it will respond differently than if there are maybe 10,000 photons in there. So that's the idea behind this description of the response and fluctuation dynamics. And we were able to measure the G2 function for small photon number with this two real eigenvalues of this matrix, this kind of bi-exponential behavior, and see the same essential behavior just with a time derivative in the perturbation response, where you kick it, it increases, and then it falls back to the stationary state. And at large photon numbers, we see an oscillatory dynamic with the same corresponding eigenvalues. And these are on either side of what is known. It's a very famous label or term in open system physics, which is called the exceptional point. So that is basically the point where your eigenvalues are coalescing. So everywhere you look, you have two eigenvalues, but only at this point they become the same. So the system somehow, basically, it has two, the eigenvectors are degenerate, if you want. Okay, finally doing this for many different photon numbers, we were able to confirm the regression theorem by showing that these imaginary and real part for the fluctuations obey exactly the same behavior as for the response. And finally, we were also able to hit the system harder and harder. And then somehow this regression theorem fails, because there's a nonlinearity. But writing down a nonlinear model and fitting the data again very nicely shows you that even in a nonlinear regime, you can observe this regression theorem using this photon condensate. So with this, let me come to the summary. I talked about optical quantum gases confined in box potentials, the fluctuation dissipation relation in the BEC, and non-Hermitian dynamics towards the end of the talk. And in the future, we are interested, in many types of new studies, and also building on the results that I showed you. For example, in the 2D gases, we are interested in what happens precisely with the correlation length at the critical point. Is there some divergence? So is there some critical exponent in the system that we can extract? We want to look at the frequency-dependent fluctuation dissipation relation and investigate in more detail the 1D to 2D crossover in these systems by having very anisotropic system traps, essentially not just one box like this, but something that is very tight along one direction. And also investigate in more detail lattices of condensates in ring-shaped geometries, which you can also see here. So these are nanostructures that we can also realize. And with this, my voice is gone. Thank you for the attention.
Yeah, thank you very much for this fascinating talk, and it's impressive to see the data quality with which you can probe all these thermodynamic quantities. So are there questions from the audience? Let's start with.
Yeah, very basic question. If I take, the standard interpretation of the ideal Bose-Einstein condensation is that the thermal wavelength becomes comparable with the de Broglie wave. Okay. Now, if you take the expression for you do a very simple exercise. You take that expression for the critical temperature and you combine it with the effective mass induced by your cavity. H bar cancels out. So, and what you're left with is a phenomenon which is not, it is called a quantum gas if you have a true massive particle. But if you do it with the cavity dispersion, it's a simulation of that. But now the role that in the original Bose gas was played by the de Broglie wavelength, so by the wavelength associated to the wave-like nature of matter. Here, that wavelength is replaced by the light wavelength, which is a classical feature. So I don't understand why. I'm not saying anything about the expander. Why call it a quantum gas? The H bar disappears.
But okay, so I didn't follow all your
if you take the effective mass from your cavity dispersion, which contains an H bar because it translates frequencies into energies, and then from the energy you express this at the kinetic energy of an effective particle, you extract the mass. That brings you an H bar into the equation, which cancels exactly with the H bar that appears in the TC expression, and so you are left with the critical temperature, which doesn't contain a H bar. So when it's light, all this phenomenology is beautiful, but it's not a quantum gas. In the same way as BC is when distance between particles becomes comparable with the de Broglie wavelength. In polariton on photon BC, the distance between the particles becomes comparable with the light wavelength, which is a classical feature, and that's what defines the critical. I mean, what would define the critical process if we were truly at thermal equilibrium. And there's no H bar. So if you can vary H bar as much as you want, the phenomenology won't change. That's my point.
Okay.
So it's not quantum. It's not a quantum. It's a classical simulation of a quantum gas, but it's not a quantum gas.
Okay, that's a very so first of all, I think I kind of agree with your point that the de Broglie wavelength you have basically, if you plug in the definition of our effective photon mass, then H bar will probably, I don't know if it will cancel.
I did this very long ago when I was working on these things.
Yeah. Okay.
It disappears.
Well, the whole phenomenology of having a de Broglie wavelength and basically being able to change this with temperature also, and then observing, for example, this turnaround point and so on of the compressibility, all this happens precisely at the point when you have your 2D de Broglie wavelength equaling your density.
Which coincides with the light wavelength.
No, it's not coinciding with the light wavelength. No, we have 1.5 micron de Broglie wavelength, and the light wavelength is 500 nanometers. So this is
there must be just a prefactor of some kind.
Yeah, there's a prefactor, but of course the mass is determined by this.
Okay. So that's the point. That's the point I want to make. So that if Isaac Asimov in his novel imagines that you can change the values of H bar. So if I came around your lab and I changed the value of H bar, I can make it 10 times bigger or 10 times smaller. The result of your experiment wouldn't change.
Yeah. Okay. I mean, it's hard to disagree.
The molecule, of course. I mean, I'm a theorist. Let's idealize. So suppose this.
There was another question in the back.
I have also more basic question. To me, I think what you showed is very similar to the laser physics. The pumping the gangling and electrochemical.
Yeah.
This is basic. What makes your experiment different from the standard physics?
Yes. So microscopically, I completely agree. There's no difference in these systems. You have stimulated emission, you have spontaneous emission, you have absorption. It's just a completely different regime of operation in terms of the parameters. So you tune this system here in such a way that first of all you retrap as much spontaneous emission as you can to keep it basically in the game. That's also something that is done in microlasers, for example. Then it's important that the medium itself actually has these thermal properties that it imprints on the photon gas. So not, well, in some sense probably every material contains information about KBT, but the question is how well does it translate to the system. And something else in terms of parameters that we really change in comparison to a laser is that we try to keep the light in the cavity as long as we can, in order to couple it more often to the molecules. And if you use a more lossy cavity, the only remedy would be to actually use more molecules, such that the absorption likelihood increases. I would basically say it's a similar system to a laser, but just operate in its regime of having the photons coupled as often as possible to the medium.
Very nice results. I have a similar question actually about the properties of the dye, because here it seems like you can use anything. Can you comment indeed on the key properties for this to work in terms of maybe quantum yield also, because there will be also non-radiative losses,
right?
Transition dipole moment, and also the Byronic fine structure. So what you say that if it's if you have just like very spaced absorption, it works so well. Or
exactly. Yes. Yeah. So there are some parameters. One would be indeed the quantum yield. So we use rhodamine dye, which has 95% quantum yield. That's kind of really high value that you can achieve. All this physics will break down eventually if you have lower quantum yield, because you will not get out the photons out of the medium. You will basically.
But this 5% in a sense loss seems to be much more or much lower Q than the cavity. So the loaded Q of the cavity, is it dropping a lot when you put the dye?
The finesse of the cavity.
Yeah, or the finesse.
Yeah, of course it will drop. Yeah. Essentially, it's dominated by the reabsorption time then. So if I have the cavity which is empty, I store the photon for a nanosecond, let's say. And if I put in the dye molecules, the photon will be gone after 10 picoseconds. Yeah. But that's precisely the regime I was talking about. We want this time to be much shorter than the lost time. So deliberately make the finesse worse.
And if there is inhomogeneities among the dye molecules in their 0.9, is it affecting the results? And how much can you tolerate of inhomogeneous?
I mean, we use vast samples with large numbers. Of course, the molecules might have some different emission properties or some structural changes, but we don't really see that. I mean, what we essentially care about, if we do spectroscopy on the material itself, it should have a significant overlap region where I can have fluorescence and at the same time absorb in this region. So the Stokes shift shouldn't be too large, but it should also not be too small. And then you can actually find out that if you take the ratio of the absorption and emission in this overlap region, it should, in the end, give you, you can calculate the temperature from that. It's basically this, I was showing the emission and the ratio of emission and absorption scales to the Boltzmann factor. If you take the logarithm and, just change the equation, you will see that you get something called a spectral temperature. And if this spectral temperature is close to room temperature, you have basically found the material that does a proper job. So we also considered like other materials, like neodymium classes, or but the dye molecules just seem to work well. We also tried perylene dye, which is also working very nicely. So it doesn't depend on this one species, but more on the spectral range and this the Stokes shift essentially.
Just a quick question from me. I mean, you've shown that you can sort of impulsively change the reservoir and affect the system by that. Could you sort of periodically drive the reservoir and think of some sort of like reservoir-driven Floquet engineered states in the system?
Yes, so actually these pulse perturbation measurements that I was showing you, we were repeating them in a different approach and having a continuously modulated drive. And we see actually that if we change then the frequency of this drive, that we can reconstruct the Fourier transform of the pulse response. So we can perform spectroscopy. But this is not Floquet, because it's completely dissipative.
But if you drive hard enough at some point, you may still see something.
Yeah, okay, well, that might be. But our approach there would be rather to be able to go and make use of an electro-optic effect or so, or Kern nonlinearity, and very rapidly change the cavity length, for example. And that will then really be equivalent to Floquet engineering.
Great. Any other questions? Otherwise, let's thank the speaker again. And